All right, in this video, we want to talk about something called the Lagrange Error Bound. And all the Lagrange Error Bound is basically it's a way for us to figure out how accurate our polynomial approximation is when compared to the real function the further away we move from the center. So let's just say we have some function f of x, we'll call that f of x. And let's say we center it at x equals 1. So in other words, our goal is to write a polynomial that will equal this function at 1 and points close to it. So maybe our polynomial looks something like that. And so maybe this is a 4th degree polynomial or a 5th degree polynomial. So we'll just call that p sub n of x. Now, the difference between our real function and the polynomial approximation is what's called the error. And as you can see, at points close to the center, the error is 0. But as you move further away from the center, the error is a little bit more pronounced. And so f of x, which is our function, minus our polynomial function, the difference between those, absolute value of those, is called the error. Some books may write it this way. They'll say that your original function, f of x, can be broken up or made up of two parts. There is your polynomial, and then there is what's called the remainder. And the remainder is nothing more than all the other terms that come after this polynomial. So let's say the polynomial is a 5th degree polynomial, has 6 terms or whatever. The remainder is the other million gazillion terms that come after that you would add to this polynomial to get an exact representation of this function. So a long time ago, a man by the name of Lagrange gave us a process by which we could see how close our polynomial approximation is to the real function. And his formula is here. And so let me erase some of this other stuff that we wrote before. And so what we have here is, and let's just break all these things down to make sure that we understand what all these pieces are, because that's half the battle right there. This is called your error. So this is your error or your remainder. Now x is the number you are trying to approximate. So we'll say that, let's just say x is the number you are trying to approximate at. And c, of course, we know by now is the center, where you're centering the function. N is the degree of your polynomial. So n is the degree of your polynomial. And then there's this next part here. This is the maximum value of the n plus 1 derivative. So let's say you have written a 3rd degree Taylor series, or Taylor polynomial rather. You would want to look at the 4th derivative and ask yourself this question: what is the maximum value that that 4th derivative could be? So what you want to do to get this error, you want to maximize this entire side here. You want to maximize it. So that means you need to find the maximum x minus c to the n plus 1 value. So let me put that in here. You want to maximize this. And you want to maximize the 4th derivative or the n plus 1 derivative, thus guaranteeing that you're getting the biggest error between the real function and the approximated function within a certain window. So let's just see how this works on a sample problem. So let's say we're given some function that has these values. F of 2 is 6, the derivative at 2 is 4, the second derivative at 2 is negative 7, the third derivative at 2 is 8. We don't really know what the function is, but we have its derivatives and its value at 6 or at 2. And it says write a third degree Taylor polynomial for f about x equals 2. So it's centered at 2, and use it to approximate f of 2.3. Well, this shouldn't be too hard for us since we've done this before. We'll just say our Taylor series says we need f of 2 plus f prime of 2 times x minus 2, the center, to the first, plus f double prime of 2 times x minus 2 squared over 2 factorial. And we need a third degree polynomial, so we need to go to f triple prime of 2 at x minus 2 cubed over 3 factorial. And so this is our approximation for f of x. And so we will now plug in f of 2, which is 6. We'll plug in f prime of 2, which is 4. We'll plug in our second derivative, which is negative 7 over 2 factorial times x minus 2 squared. And then we'll plug in our third derivative at 2, which is 8 over 3 factorial times x minus 2 cubed. And then we plug in our 2.3, goes into there and there and there. And we end up getting 6.921, and that is approximately equal to f of 2.3. That is our approximation for f of 2.3. Okay, in part A, we wrote a third degree. Let's write that down, a third degree Taylor polynomial. So maybe we'll write it as T3 of x, what we wrote, or P. We always say P, 3 of x. And now it gives us some information about the fourth derivative of f. It says that the value of the fourth derivative of x can be no bigger than 9. So we now know the maximum value of the fourth derivative. Well, that would be the n plus 1 derivative because we have written a third degree Taylor polynomial. And so in order to use Lagrange's error bound, we need to know what the maximum value of the fourth derivative would be, and they give it to us here. In the next problem, we'll see we have to figure it out, but in this problem, they give it to us. And notice we're centering this function at 2, and we wanted to see how close our approximation at 2.3, which is moving further away from the center point at 2, we wanted to know how close that approximation is to the actual value f of 2.3. So let's just plug everything into this formula for Lagrange. So we will say that our r of 3, our remainder that is related to the third degree Taylor polynomial of x, is going to be no bigger than, okay, we went through these, x minus c. All right, our x is what we are trying to approximate. So we're trying to approximate 2.3. Our c is our center, so that's going to be 2. And our n is 3. That's the degree of the polynomial. So this is 3 plus 1. Raise that to the 4th power. And that is going to be over 3 plus 1 factorial. So 3 plus 1 factorial is 4 factorial times the maximum value of the fourth derivative, which they give us in the problem is 9. So you work all of that out on your calculator, and you will get that the error that the third degree Taylor polynomial, the biggest that the error will be between your actual value and your approximated value in a certain window between 2 and 2.3, that's important, is going to be no bigger than 0.0030375. Okay, in part C, it wants us to use our answers to parts A and B to find some interval such that the real value of f of 2.3 is guaranteed to be between some lower bound and some upper bound. So we remember that in part A, we said that our approximation of 2.3, which we got from using the Taylor series, the third degree Taylor polynomial, is 6.921. In part B, we said that the error in using that third degree polynomial is going to be 0.0030375. Now, if we take that error and we add it to this or subtract it to that, it guarantees that, actually we have to add it and subtract it, it guarantees that the real value of f of 2.3 must be 6.921 plus this error, which is going to give us 6.924, and then 6.921 minus that error, which is going to give us 6.918. And so the real value of f of 2.3 is guaranteed to be somewhere within this range because of the Lagrange error bound. All right, in the second example it says, let f be the function given by f of x is equal to sine of 5x plus pi over 3, and let p of x be the third degree Taylor polynomial for f about x equals 0. So in part A, we just want to write the third degree Taylor polynomial. So we are just going to write down our f of x, which is going to be sine of 5x plus pi over 3. And then we'll take some derivatives. So f prime of x is going to be the derivative of sine is cosine. And we're going to leave the inside alone. And then we're going to multiply by the derivative of the inside, which is 5. So that's your chain rule. And then your second derivative is going to be the derivative of cosine is going to be negative sine. So negative 5 sine. And we're going to leave the inside alone. And then we're going to multiply by the derivative of the inside, which is 5. So that will turn that into a 25. Let me not do that way. Let me just multiply it times 5. And then that'll turn into a negative 25 sine of 5x plus pi over 3. And then the third derivative is simply going to be negative 125 cosine of 5x plus pi over 3. And even though we are only asked to find the third degree Taylor polynomial, I'm going to find the fourth derivative because we're going to need that because that is our n plus 1 derivative. So maybe I'll do that in a different color. That is our n plus 1 derivative. So our fourth derivative is simply going to be 625, after you do the chain rule, sine of 5x plus pi over 3. All right, so now we're going to plug in 0 because this is a Maclaurin. So we're going to plug in 0 into all of these derivative values. So f of 0 is simply going to be the sine of pi over 3. That's going to be your sine of 60, so that's root 3 over 2. And then f prime of 0 is going to be, it's going to be 5 times 0 to 0. So the cosine of 60 is 1/2 times 5, so that's going to be 5 halves. And then the second derivative evaluated at 0 is going to be negative 25 times, well, x is still 0, so pi over 3. So that's going to be negative 25 square root of 3 over 2. And then the third derivative, evaluated at 0, just comes down here. So if x is 0, you're taking the cosine of 60, which is 1/2. So it's going to be negative 125 over 2. And now that we have all of these coefficients, we can plug them into our Taylor series. So we'll say our P of 3 of x is going to be equal to f of 0, which is root 3 over 2, plus f prime of 0, which is 5 halves, and that's going to be times x to the first. And then we'll have our second derivative, which is going to be negative 25 square root of 3 over 2 factorial times x squared, because this is centered at 0. And then our third term is going to be negative 125 over 2 divided by 3 factorial times x cubed. And that is our third degree Taylor polynomial. All right, in this last example, part B, it says use the Lagrange error bound to show that our real function's value at 1 over 15 minus our approximated value at 1 over 15 is less than, or guaranteed to be less than, 1 over 1200. So once again, we see that we are trying to center our function at x equals 0, which means, by way of review, that our main goal is that our polynomial follows very closely this original function at points at 0 and very close to 0. So what we're trying to figure out is when we get slightly away from 0, 1 over 15, we want to see how close our approximation is to the real value, and we want to show that it will be less than 1 over 1200. So if you remember in the last part, we said that the fourth derivative, so f4, the fourth derivative of our function was 625 sine of 5x plus pi over 3. So we're going to need that in just a moment. So let's use our Lagrange error bound, and x is the value that we are trying to approximate. So once again, third degree, so our error, let's write that up here, our error by using the third degree polynomial is going to be no more, according to Lagrange, than x, which is 1 over 15, that's what we're trying to approximate, minus our center, which is 0, and that's going to be raised to the n plus 1 power. Our n is our degree of our polynomial, so 3 plus 1 is 4, and that's going to be divided by 4 factorial. Now this next part, we've got to say what is the maximum value of the fourth derivative. Now let's just take a look at the fourth derivative. The fourth derivative is 625 sine of 5x plus pi over 3. Well, we know that the sine graph looks like this. The highest it ever goes is 1, and the lowest it ever goes is negative 1. So therefore, the highest value that this fourth derivative could ever be, regardless of what x we choose, is simply going to be 625, because the sine will never be bigger than 1. So now we can say that 625 is the maximum value of our n plus 1 derivative. And without a calculator, we got to get kind of clever here to evaluate this. So what we'll say is, we will say 1 over 15, I'm going to break that up as 3 times 5 to the 4th power, times 625 over 4 factorial. And so now I'm going to raise both 3 to the 4th and 5 to the 4th. So that's going to be 1 over 3 to the 4th times 5 to the 4th. And dividing by 4 factorial is the same as multiplying by 1 over 4 factorial. And that's going to be times 625. And then we will recognize that 5 to the 4th is 625. So if we have to write that out, that's fine. 5 times 5 is 25, times another 5 is 125, times another 5 is 625. So we can recognize that 5 to the 4th is 625, and that is 625. And then 3 to the 4th is 81. So we essentially have 3 over 81 times 4321, which is 24. We can multiply that out on some paper, and we get 1 over 1944. 1 over 1944 is indeed less than 1 over 1200. So therefore, we have proven that the error in using our polynomial at approximating 1 over 15 is certainly less than 1 over 1200.